Okay, great. So for questions today, if you feel like you have an urgent question during the talk, feel free to just unmute yourself and interrupt. If you don't want to interrupt, then you can wait till the end of the talk and we'll do a Q&A session using the raise hand feature in the participants list. Or you can write in the chat and one of the hosts will read it for you if you prefer that. There's also still slots for one-on-one meetings later with Tyler and Jacob, so feel free to sign up for those if you are interested in talking to them more after the seminar. The first speaker today is Tyler Holland-Ashford. He got his bachelor's in physics from Harvey Mudd, and he's now a grad student in astronomy at The Ohio State University, working with Laura Lopez on X-ray observations of supernova remnants, and he's graduating next semester. So he uses X-ray imaging to study the observed distribution and properties of supernova ejecta for comparison to the predictions of 3D supernova simulations. He has analyzed data from all modern X-ray telescopes and will expand to high-resolution spectral studies with the microcalorimeter on the upcoming, I don't know how you say this,
Prism.
Anyway, that's very interesting to many of us here, I know. So Tyler, go ahead and take it away.
All right, great. Well, thank you for that introduction. Yeah, I'm happy to have this opportunity to talk about my research. And so I'll be telling you about two of my projects that I've worked on, analyzing ejecta asymmetries in core collapse supernova remnants. So the goal of my work has been to use supernova remnants to understand supernova explosions, right? These explosions are incredibly important for chemically enriching galaxies, imparting energy into galaxies through feedback, all of which affects the formation of new stars and just the general accretion onto the central black hole, and even are thought to be sources of cosmic ray acceleration. However, studying supernova can be difficult as they're pretty rare. So if you want to study a lot of them, you have to look pretty far away in distant galaxies, which limits the amount of information that we can gain from studying them. And it's still uncertain. A lot of things are still uncertain about these explosions, such as, for example, the exact relationship between progenitor scenario and type of explosion. And so supernova remnants are a way to study these things in detail as the remnant from the supernova explosion expands for 50 or so thousand years into the surrounding ISM. And so here is an image of Cassiopeia A supernova remnant, the youngest core collapse supernova remnant in the Milky Way. And by looking at these remnants that are so close and so large, we can resolve them and study them in detail. For example, here in Cassiopeia A, the colors correspond to different emission from different elements and emission processes. So by looking at the, for example, purple emission, this tells us about the distribution of iron in the supernova remnant here. Green and orange are from silicon and sulfur, and then blue is from synchrotron emission as the shock impacts into the ISM. And so studying each of these, wavelengths can tell us about the properties of the supernova remnant, which we can then kind of back evolve to learning more about the supernova explosion processes. And so one detail about supernova remnants that I study is the fact that they are asymmetric. If you look at this sample of just a random sample of supernova remnants I pulled up, you can see each of them exhibits different levels of asymmetries, both large and small scale. Right? Some supernova remnants are more circular, some are more elliptical, some are right on one side but not the other. And then within each supernova remnant, the distribution of, say, different metals, iron to silicon, are different, and you can see individual substructure in these remnants as clumpy structures or broad structures or lines, filaments, and all different types of features. And so when studying these supernova remnants, you can actually look at their asymmetries to learn more about the explosion processes. My advisor, Laura Lopez, in 2011, analyzed the asymmetries of different remnants and was able to actually classify them according to types based on these asymmetries. So she's measuring here the ellipticity and the mirror asymmetries of these remnants using higher order terms of the dipole moment, the quadrupole and octupole moment. But basically she made these measurements of these supernova remnants, compared them, and found that the core collapse remnants were systematically more asymmetric than the type 1a supernova remnants, indicating that there was some physical mechanism that caused a higher degree of asymmetries in core collapse than has happened for 1a supernova. And so quantifying the remnants, quantifying the properties of remnants is important. So you can compare them and analyze them as populations, and they can reveal broad trends such as found by her. So my work has involved quantifying supernova remnant asymmetries and then comparing those to see the predictions of 3D simulations in order to test the supernova mechanisms and the progenitor scenarios analyzed in those 3D simulations. Here, I want you to focus on this middle image here, which is the result of a very recent 3D simulation, as it's really only in the past 5 or 10 years that simulations have advanced to the point where they can evolve through explosion and to thousands of years later, supernova remnant. A huge feat given the incredibly different spatial scales that you have to care about during explosion, and then it over parsecs as the supernova remnant expands. And so here's a very recent paper by Orlando et al. 2020, which modeled a Cas A-like supernova remnant. And this image is showing the distribution of iron as it's expanding and running into the reverse shock, which is this yellow shell, which is kind of moving inward. And you can see that there's kind of three plumes of dense iron emission, which is then starting to extend into fingers of emission as it gets disrupted by the reverse shock. And this matches up pretty well with what we actually observe in Cassiopeia A, this right image here. Again, you see these three plumes with these kind of fingers kind of protruding and extending out as it gets disrupted by the reverse shock. But as I said, it's important to do more than just visually compare simulations to observations. It's important to quantify the asymmetries. And so the first project I'm going to tell you about is my work on analyzing supernova remnant asymmetries and comparing them to neutron star kick velocities. Neutron stars, one type of compact object left over from core collapse supernova, have been observed to have velocities of hundreds to possibly even thousands of kilometers per second in some cases, velocities that are much too high to result from the disruption of a binary that the progenitor star was in. And if it can't be from disruption of a binary, it has to become from explosion processes. And the two dominating theories for how these neutron star kicks are generated are conservation of momentum arguments, either conservation of momentum with anisotropic neutrino emission, the bulk of neutrinos move one way and the ejecta and the neutron star move the other way, or simply conservation of momentum with the ejecta, kind of an opposite case where the neutron star now moves opposite the bulk of ejecta motion. And most simulations in theory have come down on the side of conservation of momentum with the ejecta, such as simulations by Wong, Muller, Yanka, who have done 3D simulations and successfully generated neutron star kicks of hundreds of kilometers per second, moving opposite to the bulk of ejecta. Here's just two diagrams from one of their simulations, where you have the bulk of ejecta moving kind of downward and the neutron star kick moving upward, as in what they call the gravitational tugboat mechanism, where the neutron star is accelerated toward the slowest moving ejecta. So you have the bulk of fast ejecta moving away from it, and then it's accelerated towards small clumps of slow moving, least energetic ejecta. And so my first project involved testing this prediction to see if the mechanism they used was actually observed. The predictions of the mechanism were actually observed in a sample of supernova remnants. So I selected a sample of young supernova remnants, so they hadn't had much time to be affected by any interactions with the ISM, so that all the emission would represent ejecta emission and from the supernova explosion. And obviously they had to have detected neutron stars, so I could measure the direction of neutron star kicks. And I compared the asymmetries to neutron star velocities to test this prediction. So I'm not going to talk much about the details of the analysis, but I do feel it's important to mention the methods of estimating neutron star velocities. The simple, most basic way is to actually calculate the neutron star proper motion, right? See it as it moves across the sky. And so this gives you, a accurate measurement if you can actually have enough baseline, if you can have a long enough baseline to actually see the motion and resolve it. And for what I found was that for the using Chandra telescope, which is the best spatial resolution of X-ray telescopes, this was only possible to make these measurements for the closest supernova remnants with at least a 10 to 15 year baseline. Kind of difficult to do in some cases because Chandra's first light was in 1999. So doing this project in 2017, only a few supernova remnants had actually had this long baseline of observations over which to observe the neutron star motion. So another method, if you can't actually measure the neutron star motion, is to use an explosion site estimation method, where you try to get a handle on where the explosion site of the supernova remnant, and thus the origin site of the neutron star, is. And so one way that people have done this is to measure the motion of a lot of different ejecta filaments as they spread outward from the supernova remnant, and then back evolve them to a central point. And now you have a central, the origin point, you have the current location of the neutron star, and an age from the supernova remnant age, which gets you a velocity. However, I do want to mention that a lot of neutron star velocity measurements have been made using a pseudo explosion site estimation, where you kind of just assume that the geometric center of the either X-ray or radio profile of the supernova remnant is the explosion site, and not using any, back evolved ejecta filaments. And so this kind of assumes a certain degree of asymmetry to your remnant. You're assuming that it's expanded evenly on all sides, and so can be an improper method of measuring the explosion site, and might give you a neutron star velocity that is a factor of 2 or 3 off from the true velocity. But so anyway, using all the criteria I've discussed, I obtained a total of 6 supernova remnants and measured the direction of bulk ejecta as measured by the dipole moment, and compared that to the direction of neutron star motion to test this prediction that neutron stars should move opposite to the bulk of ejecta, assuming an asymmetric explosion mechanism that results in conservation of momentum between ejecta and neutron star. And I found a pretty striking result where here in this plot, I'm showing the sample of my supernova remnants and the angle difference between the neutron star motion and the ejecta direction. And for 5 out of the 6 supernova remnants I analyzed, the neutron star was indeed moving almost exactly opposite to the bulk ejecta motion. And this 5 supernova remnants up here, consistent with this scenario, consistent with conservation of momentum and the gravitational tugboat mechanism used in simulations, and implying that the physics they used was, if not correct, at very least consistent with the observations of actual supernova remnants. Briefly, I just want to mention RCW 103. You see this supernova remnant has kind of the opposite correlation. The neutron star seems to moving directly with the ejecta. So if true, and this is not like an error from calculating the proper motion, this could be very interesting, especially since RCW 103 has not only a magnetar in it, the neutron star is a magnetar, it's also a very weird period magnetar with a period of 7 hours, which is orders of magnitude higher than any other magnetar that we really know of. And so that might have something to do with why the neutron star is moving with the ejecta, and might provide support for this anisotropic neutrino emission as opposed to the conservation of momentum with ejecta. So this was my first project, and in my second project, I tried to test some of the more detailed predictions of these asymmetric explosion mechanisms used in simulations. So for these asymmetric explosion mechanisms predict that heavier elements should be more asymmetric than lighter elements, as these heavier elements are formed predominantly during the explosion, whereas lighter elements such as oxygen are formed predominantly in the post-main sequence burning, and should exist in shells decently far away from the center of the star, from the core explosion site. And also similarly, the neutron star kick should be most opposed to these heaviest elements, most opposed to the elements that are formed closest to it, and exhibit the highest levels of asymmetries. And so in order to test this, I focused my analysis on a single supernova remnant, the Cassiopeia A, which has the most observation time of really any supernova remnant, using this remnant as kind of a test case to see what level of detail I would need to make these measurements for other supernova remnants. And so the simple method of looking at different ejecta in supernova remnants is to take all the flux that corresponds to a certain range of emission lines. For example, here I'm showing silicon, sulfur, and iron, and create maps from all the photons in those ranges, and you get something that looks like these maps here, which you can see slight differences, like iron, for example, has these three plumes that are brighter than the rest of it, whereas sulfur and silicon seem to be more broadly distributed. But problem with doing it this way is that you're also including continuum emission, all the broad thermal and possibly synchrotron emission that encompass the bulk of this spectra, and not just the emission from the element in question. And so the way to fix this is to perform continuum subtraction, fit as many regions as you possibly can in the supernova remnant. You extract and fit the spectra. Here's an example spectra shown here. And then you have the total fit minus that of the continuum, should just give you in each energy range the emission that corresponds to each element in question. So silicon, sulfur, argon, calcium, iron, and magnesium are some of the most prominent lines that you can get. And I just want to show you a brief image of what the differences between the bandpass method and continuum subtracted method look like. So here is a plot that I produced containing the map for continuum subtracted iron emission compared to the just taking all the photons in that range and not correcting for the continuum. And there's this significant difference between these two, right? In this one, you see clearly the three plumes of iron with not a lot of the broad continuum emission that is present throughout the remnant, and which matches with the simulations and also other observations, which find in Cassiopeia A this three-plumed structure of iron in Cassiopeia A. So creating these maps for all the elements I mentioned, I then measured the asymmetries for each of these elements. Again, going back to the quadrupole and octupole asymmetries, measuring how elliptical you are and how mirror asymmetric you are if you flip across the central axis, and compared them for each of these elements. And again, came up with a striking result that exactly matched the predictions of these simulation papers, where the heavier elements, the elements that are formed predominantly during explosion, have much higher asymmetries than the lighter elements. Again, here on the y-axis, higher is more elliptical, and then the x-axis, higher is have more mirror asymmetries. And it seems like, right, you can group these by the burning process, whereas your levels of asymmetry is largely determined by how much of each element is created during post main sequence burning versus explosive burning during the explosion. And so I want to just quickly compare the method of doing this analysis on continuum subtracted images to that of doing it on the bandpass images where you do not continuum subtract. And for this bandpass analysis, you still get the general trend where heavier elements are more asymmetric, but everything has been brought closer together. And especially for elements with similar levels of asymmetries, there's no longer this one-to-one correlation where you go from lower masses, lower asymmetric to higher mass is more asymmetric, as shown in this continuum subtracted analysis. So if you want to get the bulk trends, you can use this bandpass method, but if you want to get detailed asymmetries for elements produced by the similar burning processes, you need to perform continuum subtraction. And finally, the second prediction of these asymmetric explosion mechanisms is that the neutron star should be kicked opposite the bulk of, or most opposed to the heaviest elements. And again, I find exactly as what was predicted by 3D simulations. Here zoomed in to the inner arc minute or two of Cassiopeia A, where the neutron star is moving downward away from the explosion site, and it is most opposed to these heaviest elements, these iron, argon, calcium, and titanium, whereas it makes a smaller angle with the lighter elements, oxygen and silicon, again providing support for this predictions of these asymmetric explosion mechanisms. So in sum, through these two projects, I have shown that supernova asymmetries can be used to test explosion mechanisms, as I found that neutron stars are indeed kicked opposite to the bulk of ejecta in a sample of supernova remnants. And in a single supernova remnant, I've shown that heavier elements are more asymmetric than lighter elements, and the neutron star in Cas A is kicked most opposed to the heaviest elements, providing support for these asymmetric explosion mechanisms, this gravitational tugboat mechanism used in simulations, and indicating that asymmetric explosion mechanisms are required for any like supernova explosion, at least core collapse, that you want to model. And so there's a lot of potential for future work, very similar to and just in general studying supernova remnants. So going off this work, a nice sequel would be to study the different element asymmetries in a larger sample of supernova remnants, so not just Cassiopeia A. And this is my current project. And I will also be not just analyzing core collapse supernova remnants, as all I've talked about so far, but also seeing if these trends hold true for type 1a supernova remnants, right? Type 1a supernova remnants, as my advisor Laura Lopez showed before, are more symmetric. So maybe this asymmetric explosion mechanism isn't as strong, or maybe it's only present in double degenerate as opposed to single degenerate scenarios. So that will be interesting to find the conclusions of. And in addition, I will, to do that project, and also just in general, the field of supernova remnants will be hugely advanced by the launch of the XRISM telescope in 2022 with its microcalorimeter. The microcalorimeter will have a spectral resolution of about 7 EV as compared to the hundreds of EV spectral resolution that is on current CCD images. So here is a example spectra from conventional telescopes from your Chandra, your XMM Newton, which can't resolve the individual emission lines, but instead you get this broad emission lines, whereas XRISM will be able to really look at these individual emission lines, able to measure the emission line, each individual emission line, giving you a handle on ionization states, allowing you to create 3D ejecta maps, which will enable us to robustly analyze the 3D profiles of supernova remnants, and generally improve our ability to analyze supernova remnants, analyze the abundances in supernova remnants, and compare these to supernova simulations and increase our understanding of supernova explosions. And with that, I'll leave you with the conclusion slides, and thank you for your time.
Thanks, Tyler. Let's give him a round of applause with the clapping hands emoji under the reactions menu. Yeah, that was really cool. Does anyone have any questions? If you do, click the raise hand button in the participants window. Sebastian, go ahead.
Yes. Hi, Tyler. Very nice
Hello.
talk. I had a question about what you were talking about your first project.
Okay.
The magnetar, right?
Yes.
How do you know there's a magnetar, and B, how do you know the period? Like, what methods are you using to find the period?
So this had been in like literature papers. I haven't done any specific analysis on this remnant, but you can find out it's a magnetar as it will have much stronger magnetic fields, and I don't think it's actually like usually pulsars and pulsar wind nebula or pulsars create a pulsar wind nebula around them as their emission kind of expands in the surrounding medium. I don't think there's actually that of a significant one for the magnetar in RCW 103. So I'm not, to answer your question about how they determined it was a magnetar, not exactly sure, but I mean, it has to do something with measuring the magnetic fields.
Okay.
I mean, magnetars have 10 to 14 to 15 Gauss as opposed to regular pulsars, which are 10 to the 13 or 12.
Yeah.
And then the period, you can check that from pulses, just see how regularly it pulses, and it's pulses at about 6.67 hours, again, compared to the 1 to 10 seconds of typical magnetars. And people have tested if this is actually coming from, they were like, okay, that's really weird. Maybe this is actually a, in a binary, and what you're actually measuring is the period of that binary. But it doesn't seem like it. It seems like that's the spin period of this object. and it is just a very weird object.
Cool. Thanks.
Yeah, no problem.
We have a question from Randall. Go ahead.
Great talk, Tyler.
Thank you.
Very interesting stuff. Regarding the asymmetries, I mean, in some sense, you might imagine that the asymmetry isn't hugely unexpected, just because being perfectly symmetric would be hard.
It's true.
Is there any information about how asymmetric? Is there a distribution of asymmetry amounts so that some explosions are more asymmetric, or more, essentially is the distribution of neutron star kicks or the amount of, so we can start quantifying just how much does it vary, or are they typically all about the same amount of asymmetries?
That's a great question. So in summary, your question is what is the spread of asymmetries in supernova remnants? And I mean, so that has been somewhat analyzed. Like, for example, my advisor, Laura Lopez, made this plot, which was able to show that, core collapse remnants are more asymmetric, and they seem to, comprise, this parameter space in how elliptical they are and how mirror asymmetric they are. So seemingly very, not much range in ellipticity, but a decent range in how mirror asymmetric they are, spanning a little order of magnitude or two. But yes, of course, you were right that there are, each supernova remnant is different, and getting a handle on the individual asymmetry, or getting a handle on the spread of asymmetries, would be interesting. So that is definitely what I plan to continue working on. Like, for example, I mentioned measuring the different element asymmetries of different remnants, but in general, yeah, as you suggested, getting a handle on the spread of asymmetries for each class of supernova remnant, because it'd be interesting to, once we measure these asymmetries, compare them to types, or comparing them to neutron star kicks. I think I have a neutron star kick distribution. Yeah, so here's measured neutron star kick velocities. So it'd be interesting to see if, for example, type 2b supernova remnants were more asymmetric than type 2p, or etc., or if this correlated with the neutron star kick velocity. In my sample of 6, I wasn't able to find a trend where between neutron star velocity magnitude and asymmetry, but this was only a sample of 6, and in the next 5 or 10 years, this will expand our ability to measure neutron star kicks to probably 20 supernova remnants in total, and so getting a sample of that size will help us answer that question.
Great. Sorry, Anna, I see you have a question, but we're out of time. We got to move on. So I hope other people will follow up with Tyler over email or sign up for a meeting. And I'll hand it over to Tatiana for the second speaker.
Hi, everybody. So just a reminder, the meeting is being recorded, so to be posted on YouTube. So if you have any objections, please let us know as soon as possible. So our second speaker is Jacob Luhn. He received his bachelor's degree from the Ohio State University and is now a 6-year NSF graduate research fellow at Penn State University under advisor of Jason Wright. He is especially interested in the detection of exoplanets using the radial speed method, and particularly in using extreme precision velocity data sets as a tool to understand stellar astrophysics. So Jacob, we're ready for you. Thank you.
Great. All right, yes, so thank you for having me. And as you said, my name is Jacob Luhn. I'm a grad student at Penn State University. And today I'm going to be talking about some recent results, as well as some upcoming results relating to the evolution of stellar radial velocity jitter, building toward an astrophysically motivated predictor of stellar RV jitter. And just to jump in with some background, for a long time, if you wanted to find a planet around a distant star, the predominant method of doing this was looking for periodic red and blue Doppler shifts in the absorption features of these stars, looking for, or due to the gravitational tug of an orbiting planet. With the launch of Kepler and the extended K2 mission, and now TESS and its extended mission, we've entered the transit era, where most of our planets are now being discovered through the transit method, which I'm showing here, where we look for periodic dips in brightness when a planet passes between its host star and our line of sight. But despite the fact that most of our planets are now being observed or discovered through the transit method, the radial velocity observations are still as important as ever, and this is because of the additional role of transit follow-up. This is used to confirm or reject transit candidates, as well as measuring masses from the radial velocities, which we combine with the radii from transits to estimate planet densities. But with this additional role comes additional strain on our RV resources, and there are simply more planets than we can reasonably follow up. And so it's important that we're able to better prioritize and select our targets so we can select the best targets and maximize our science return. And to do this, we can use the fact that some stars are simply intrinsically better suited for radial velocity measurements than others, and this is where RV jitter comes in. And so in short, RV jitter is any radial velocity variation induced by stellar variability. So this is intrinsic stellar variations. These can be driven by magnetic activity, such as star spots, faculae, flares, or long-term activity cycles, and can also be driven by convection, like granulation on the stellar surface, as well as stellar p-mode oscillations. Now, a lot of work has been done in the past on radial velocity jitter, and from this, we've learned that RV jitter increases with activity, and I'm showing one example plot here, where we see that for different types of stars, RV jitter increases as stars become more active. And the interpretation here is that as these stars increase in activity, they're more likely to have spots, faculae, flares, etc., that can be rotationally modulated and increase the radial velocity variability. On the convection side of things, we've also seen that RV jitter increases with evolution. And so I'm showing here now a plot of RV jitter measured by the root mean square as a function of the surface gravity with more evolved stars to the right. And we can see that as stars evolve, they increase in RV jitter. And the interpretation here is that as these stars evolve, their convective power increases. And so the amplitudes of granulation and oscillation also increases. So my work has been focused on determining which stars have jitter that's dominated by convection and which stars have jitter that's dominated by activity. And to do this, I measured the RV jitter of a sample of 600 stars from the California Planet Search and measured their jitter, which I'm showing here with RV jitter, again, as a function of surface gravity with more evolved stars to the right. These points are also color-coded by activity, so more active stars are in yellow. And from this plot, we see two distinct features. The first is this vertical pileup of active stars at high surface gravities. These are surface gravities near their zero-age main sequence where they were born. And then there's also this more horizontal floor of inactive stars that shows a gradual increase with evolution. And so what I've empirically identified here are these two regimes, these activity-dominated stars and these convection-dominated stars. And in fact, what this plot is telling us is that RV jitter tracks stellar evolution. And so what we find is that a star is born and it's rapidly rotating, and that rotation combined with a convective envelope generates a magnetic field. And so it's very active and jittery. As it lives its life on the main sequence, it loses angular momentum through stellar winds. It spins down and decreases in both activity and therefore jitter. It continues to spin down until it falls to a jitter minimum, where it transitions from activity dominated to convection dominated, where it goes through a gradual increase from convection as it evolves into the subgiant and then later giant regimes. Now, you might notice a number of high points that don't fall along this general path that I outlined. And for that, I'll simply say that when measuring the RV jitter for these stars, we have to remove any Keplerian signals or center mass motions to isolate just the intrinsic stellar variability. And so many of these high points come from unsubtracted planets that we weren't able to constrain fully. But not all of these high points come from unsubtracted planets, and so there's more to the story that I haven't yet covered. And as we know with stellar evolution, it depends heavily on stellar mass, and so we expect the same would hold true for the evolution of RV jitter. And indeed, when we break our sample up by mass, we find that the jitter minimum depends strongly on mass, with more massive stars hitting their jitter minimum at later evolutionary stages. And I'm just showing that on the left here, broken up by different mass bins. And you can see that this transition from activity dominated in the vertical portion to convection dominated in the more horizontal portion becomes smoother as you go to higher masses. And this is simply a result of stellar evolution. So more massive stars are evolving more quickly, and they're moving to the right more quickly on this diagram as they're still spinning down or in the final stages of spin down. But additionally, compounding this factor is the fact that the most massive stars in our sample are above what's called the Kraft break. And so these stars have very thin or non-existent convective envelopes when they're on the main sequence. And it's not until the subgiant regime that they're able to develop a convective envelope, generate a magnetic field, and then spin down. And so these the most massive stars in our sample undergo a delayed spin down. And so from all of this, we've seen that RV jitter depends strongly on its activity, its evolutionary stage measured by surface gravity, and also the mass. And so we have already now the building blocks to estimate or predict the radial velocity jitter based on this astrophysical picture. But before we jump to that, I wanted to focus for a few minutes just on another interesting result, which came from looking at the RV jitter of F stars. And now these are interesting targets since they are typically avoided in radial velocity surveys because of their high expected jitter from rotation and therefore activity. What we found is that in a small subsample here of 1.1 to 1.2 mass stars, that there do exist some low jitter F stars that are stable to 5 meters per second or better. And so it was our goal then to identify, see if we can distinguish which F stars were low jitter and which F stars were high jitter. And so I'm just showing a color magnitude diagram here showing our whole sample, and in particular in green, the F star sample. But from this astrophysical picture that we just built, we can use the insight that high jitter stars will either be active or they will be evolved. And so I developed a simple jitter metric that combines these two terms, an activity term, and then a proxy for evolution using the absolute magnitude in the Gaia G band as a jitter metric to probe the jitter for these stars. And as we can see here on the right, when we plot RV jitter as a function of this jitter metric, it does a rather good job of distinguishing the high jitter stars on the right from the low jitter stars. And you can draw different thresholds in this jitter metric depending on if you're selecting a pure or a complete sample of low jitter F stars. And just as a point of reference, if we were to only use, say, an activity term, this is what the plot would look like. And you can see that it's not nearly as cleanly separating the high jitter and the low jitter F stars. And again, I want to emphasize that this was developed and made to separate the high and low jitter F stars. But as we found out, this actually works for all of the stars in our sample, not just the F stars. And it actually has some predictive power as well, as you might be able to guess from this plot. And so here now I'm plotting RV jitter as a function of this jitter metric again, but now for all of the sample of the stars in our sample. And you can see they're color coded by mass, and with a simple fit to the low jitter metric stars below 1.5, we can build a predictor, a very simple jitter predictor that can predict jitter to median percent error of about 27%, which is a significant improvement over similar empirical estimators such as Wright 2005, which was good to about a factor of 2. And so this is a good start, but we want to go one step further and build a more astrophysically motivated predictor of RV jitter. And so to do that, I've built a hierarchical Bayesian model, where the jitter is composed of 4 terms: an activity term that depends on the log r prime hk activity, stellar mass, and the v sine I, a granulation and an oscillation component that both depend on the effective temperature, surface gravity, and the radius, and then an overall instrumental term that's the same for every star that comes from the Keck high-res instrumental uncertainty. And to ensure that we're fitting actual astrophysical components, we can use the fact that for granulation and oscillation especially, these have theoretical scaling relations from, for example, Kelton and Betting, 2011, that we can use to place priors on the hyperparameters in this model. And just as a confirmation of these scaling relations, here I'm showing for a single star cleanly resolved stellar p-mode oscillations. So this isn't a planet curve, this is stellar oscillations from astroseismic observations. And we see that the expected amplitude from these scaling relations almost exactly match the best fit sinusoid. And so this is just a confirmation of these scaling relations. And then the additional thing that we can account for in this model is the uncertainties that go into the input stellar parameters. So we can account for those stellar uncertainties as well. The last piece to this model is our choice to fit the jitter floor. I mentioned earlier how any unsubtracted planet will cause an inflated measurement of RV jitter. And so we introduce an upward scatter S term that's drawn from a gamma distribution, an asymmetric gamma distribution, such that the true jitter is just S+1 times the jitter floor that's calculated above. And the exact size and shape of this asymmetric gamma distribution is left as free parameters in our model. And to give a sense of what that distribution looks like, I'm showing here the posterior with each individual sample in gray and the median in orange for this gamma distribution. And to be a little more explicit, this is then showing the distribution of this true jitter in units of the jitter floor. So now that we have this model, how well does it work? So here I'm showing the RV jitter as a function now of log r prime hk, so activity color-coded by mass. This is the data that we're fitting with this model. And now on the right, I'm showing our fit model with the same data from the left underplotted in gray. You can see that we do a very good job reproducing the bulk trends in activity as well as mass. But this is our ability to fit the data with this model, and we want to use this fit to predict RV jitter. And so this is maybe a little misleading. And so we need to then sample from that posterior and account for and use the input stellar uncertainties in those parameters to then predict RV jitter. And by doing so, then we can get a probabilistic RV jitter with RV uncertainty, or with uncertainty that comes from the uncertainty in the hyperparameters shown there on the left, and then also those same input stellar uncertainties. And lastly, that scatter above the floor term that will accounts for any unsubtracted planets. And so once we do that, our results look like this. And you can see it still does a very good job, not quite as clean as our ability to fit the model, but for, in this case, this is one posterior sample. You can see that it does, again, still a very good job reproducing the overall bulk trends that we see. And to show exactly how well it performs, I'm showing here the absolute fractional error of our predictor as a function of stellar mass. And for most of the stars in our sample, we can predict to about 20 to 25% error. If you compare that to the previous simple jitter predictor that I mentioned before, that was good to about 27% error, it might not seem like much of an improvement, but I'll remind you that that was used just for the low jitter or low jitter metric stars, whereas this models all of the stars in our sample. And additionally, because of the way we built up this models individual components of RV jitter. And so a natural data product is to get the expected amplitudes for activity, granulation, and oscillation, which can be really useful for informing future observations. And so I'm working on putting this all together as a tool for the community that will allow users to predict RV jitter given input stellar parameters. And it will return individual components of RV jitter for the astrophysical floor, as I mentioned. So it will give the oscillation, granulation, and activity components. Additionally, users can input their own probability density functions for the stellar parameters that they wish to predict. And then lastly, because we included that instrumental term in our model for the Keck high-res instrumental floor, we can remove that and swap that out for another instrumental uncertainty to allow translation between instruments. And so with this now, you can see how this could be, will be very useful for the community in informing not only the best targets to select and prioritize, but also informing exact observation methods to mitigate these different components. I haven't gone into it in this talk, but lots of work has been done on mitigating individual components, say activity versus granulation and oscillation. So if we know a priori that the oscillation component for a given star is expected to be the dominant component, that will affect how we choose to observe the target. And so lastly, then in my final few minutes, I wanted to take a step back and talk about some of the limitations of this model and then how that affects future next steps. Oh, and right, I forgot to say, this is still under development, so it's coming soon. But currently, where we have the most, or the strongest limitations comes from the Keck high-res instrumental floor, which is about 2.5 meters per second. And so predicting jitter below 2.5 meters per second is relatively uncertain compared to anything above that. Additionally, we have a lack of low mass stars, and the trends that we see is that these low mass stars are potentially the best targets for radial velocity observations as they have the lowest levels of jitter. And so my next steps, I'm very interested in building up a sample potentially with HARPS North or HARPS that have similarly long time baselines as Keck high-res, California Planet Search Survey, but have instrumental precision down to the meter per second level. And so we can really probe in this gray region here, and also as has been leveraged by many people at the CfA, has been used to follow up observations on particularly M dwarfs from TESS. And so these two samples then could really help develop a more robust predictor of RV jitter. And so I'm very interested in seeing some of the results there. Okay, and so lastly then, I just wanted to wrap up and go through my conclusions. So I showed that radial velocity jitter evolves from activity dominated to convection dominated, with more massive stars reaching their jitter minimum at later evolutionary stages. I showed that low jitter F stars exist and can be distinguished, and that the jitter metric used for F stars also works for other stellar types as well. And I'm working to build this tool to predict jitter for a wide range of stars that models individual components of RV jitter so that we can inform target selection and prioritization for these stars, but also the observing strategies so that we can mitigate individual components based on our either observation strategies or also, I didn't talk about this too much, but also statistical analysis after we get observations. And so hopefully this will be a very useful tool for especially things like test follow-up. And so with that, I will stop and take any questions that you might have. Thanks.
So please, let's first thank our speaker. You have the emoji reaction with the clap hands. And yes, you can use both. You can click and raise your hand so I can ask the question. At this moment, we have a question written on the chat. The question is saying, what observable are you using to measure activity?
Right, the primary observable that I'm using right now is the log I prime HK. So this comes from the calcium H and K emission features. Yeah, I know that things like HARPS and HARPS North, those are not quite as, not used quite as frequently. And so perhaps translating from one to the other, it might be useful to look at something like H alpha as well, but I haven't looked at H alpha at all in this work. It's mostly been the calcium H and K emission features.
So yes, David Phillips, please, can you?
Very nice talk. That's a whole lot of stars you're modeling at one time. On the other side of that, do you have to worry about overfitting at all with your model? It seems like it has a lot of parameters, even though presumably there's a lot more stars. It just, I was surprised by how many parameters you had in your model. Is overfitting an issue?
I think that it certainly could be, and that's another reason why I'm very interested in expanding the sample. Yes, so there is a lot of flexibility in this model, especially when we incorporate the that upward scatter term. And one of the things that I didn't get into with this was also by incorporating the stellar uncertainty parameters, or the uncertainties in the stellar parameters. One of the things that I struggled with for a while, it was basically just, it preferred to adjust the true stellar parameters, and it could get it essentially bang on, and it was moving towards unphysical parameter spaces. So either very low mass stars that were very evolved, which we don't have in the age of the universe isn't long enough for those stars to be that evolved, or also very high mass stars at high surface gravities that are not near their zero age main sequence. So I did have to constrain the parameter space for the stellar uncertainties. But yes, I think though that because we're using, or we're anchoring the granulation and oscillation components on these theoretical relations, that that we are still modeling astrophysical components, although we may be overfitting to some degree. And so yeah, I would really this is sort of a good first step, and yeah, I'd like to continue building up the samples. Part of the issue is that the sample is so big and spans a wide range of parameter spaces that, or parameter space, that some areas of parameter space are emptier than others, and so there are some gaps there that it could be really nice to fill in.
Is there another question? Okay, let's thank again our speaker. Thank you so much, Jacob. It was very interesting. I love that it's a public code. Let's see what people is going to collaborate with you. And again, to all our attendees, I would like to say thank you as well. This is possible because of you. And please, if you want to talk to Jacob, do not forget to use the one-on-one meeting. He is available today, so just check out his schedule. And thank you, everybody. Remember that the meeting is being recorded and it's going to be posted on YouTube. So if you have any objections, please let us know as soon as possible. Thank you, Jacob. Thank you, Tyler. Thank you, everybody. Take care.
Thank you.